Okay, good morning. Is this the normal number of people on Wednesday, or just only today? I'm not back from my last year. Okay, so as you asked, we moved the lecture to Wednesday. So we're going to have a targil on Monday again, because I'm not quite back yet, and then another class next Wednesday, another lecture. But then we'll go back to the normal times, which means I'll have 4 hours, and Noga will have a lot to do in between. So we're going to move the next Wednesday is another lecture, and then 2 weeks from now it's going to be a recitation of class Targil again. So I hope all of you read the lecture notes of the third lecture notes of Amir on parameter estimation. At least I'm going to assume that. If you didn't, it's about time that you take me seriously about it, because I'm really going to use the fact that you read it and you understand it, and you just have to ask questions. Israeli students especially are not used to read before the lecture. What does it mean? Well, that's what they expect. So any questions or comments on the lecture notes? Obviously everything is clear. So,
can you explain what a conjugate prior is?
I can, but it's not right now, and it's not terribly important actually. It's a technical thing that statisticians made a lot of fuss of, but it's essentially just a convenient prior, in the sense that it couples well with the parametric family, such that things like maximum likelihood or maximum posteriori actually can be calculated easily. We'll actually see later on in the course some more interesting aspects of prior, but since priors are more or less arbitrary, at least when we talk about parameter estimation, we can choose them as conveniently in some sense. And conjugate priors is one way of doing it. It used to be much more important 30, 40 years ago than it is today. Nobody is really using conjugate priors for anything. But some theoretical analysis, something you want to have a prior, and you choose one which is convenient. That's essentially all it is. We'll actually, later on, next week sometimes, or maybe I'll talk about something else which is known as the Jeffreys prior, or the most uninformative prior in some sense. I think that assumes less than anything else, and this is actually an important concept, so I'll come back to this. And in some cases, actually, the conjugate prior is a Jeffreys prior, is a least informative prior, but that's something we'll see when I talk about information and estimation. So, just to remind you, we started to talk about parameter estimation. The general problem of estimation is really the inference of a statistical model from observation. Not in the restricted sense that we talked about so far, which was decision making, but in a somewhat more general sense, which actually allows us to cast into decision making a much more general problem, which is estimating the model. And then I start to talk about all sorts of properties of such models, and so this is the next natural step in some sense in the story of Bayesian inference. So we actually talked about the following analogy, if you want. So we assume that we have a parametric family over some random variable x. Sometimes we write it as, especially the non-Bayesians write it like this, as if it's really a parameter of the distribution. Sometimes we write it as f, which is just a standard notation for density function, but it's the same thing for me. And in general, what we assume is that we are given some set of parameters. So theta, which can be, again, multidimensional, lives in some subspace, which we call sometimes denoted by capital theta, which we generally assume is some subspace of some RD. D is usually the dimensionality of the space of parameters. So we usually assume real valued parameters that live in some compact, continuous, not necessarily compact, but continuous subspace of R, of some multidimensional R. So this, of course, can be many other things, but this is the setting we're thinking about. Continuous parameters that live in some connected space of the real value. And those parameters, we actually want to assume that this family or parametric family of distributions is what we call sometimes identifiable. So those of you who actually read the notes should know what it is. I don't find it anyway. So when we say identifiable, so we assume that the parameters define the distribution uniquely. So there are no two distributions, or we cannot parameterize in two different sets of parameters the same distribution. Or in other words, we assume that if px of theta 1 equals px of theta 2 as distribution, which means this is true for all x's, this can happen if and only if, in some sense, theta 1 equals theta 2. So this is what we call identifiability of the family. It's not obvious, actually, so in many cases, it's not easy to see if that family is identifiable, especially when the parameters there are many parameters and they're related to each other. For example, neural networks, multi-layer neural networks, let's say, are usually not identifiable in the sense that we can have many different connections. If we think about the connection between the neurons as the parameters, there are usually many different networks that media exactly the same map. Yeah, I mean, usually there's a lot of redundancy there. You can shuffle the neurons, you can permute them, you can take any linear transformation of the weights between the layers, it will not change anything, as long as they have one-to-one transformations. So there's a lot of non-identifiability there. That's one of the problems of neural networks in general. But even other types of models, for example, Hidden Markov models that we mentioned already, it's not obvious that they're identifiable. You need to prove it. And it depends on exactly the parametric form of the output and the transitions. And so many other things. There are many, many classes that are not identifiable. But so this seems like a very natural and very naive assumption. It's actually not so obvious in many cases. So in other words, usually we like to say that if the KL divergence between these two distributions is 0, which is essentially this, but as you know, up to a measure 0 set for this 2, 1, 2, 2, then this is essentially if and only if the two parameters are the same. Of course, both of them belongs to this class theta. Okay, so that's essentially my working definition of identifiability. So if you want, this is the definition of something we call identifiability. Of the model. Okay. Identifiability, something like this. So under this assumption, we usually assume the following setting of the problem. I mean, we have some parameter, which is taken from this possible set of parameters. And this parameter is going to generate observations as a Markov. So whether you assume a prior or not doesn't matter at this point. Either there's a fixed parameter and you don't do anything about it, or if I'm a Bayesian, there is a prior here, with which I actually sample the parameter. But that doesn't really matter at this point. But what I definitely generate statistically is observation X through this conditional distribution, or parametric distribution. So this is what we mean by that. In most the cases we are interested in at this point, this X is actually what I usually denote as a sample, a set of samples taken, in most cases that we talk here, IAD. So I independently sample the distribution Px of theta for a given theta. So this is what we call the IAD sample here. So the observation is, a special case of the observation is IAD sample of size n. N can be any integer. And this makes life a lot easier in many cases, you already saw, if you assume independence. But in many cases, this assumption is not exactly correct. And I would like to have results which depend on that, or independent of that as much as possible. So, but as usually the interesting things are happening with this assumption, even in what we call the larger limit. That's totally the large sample size. This is most of the things I'm going to discuss today. So, of course, the assumption is that there is a variable which is a function of the sample, function of observation, which we call the estimator. So this is going to be a function of my sample, or sometimes I'll simply write theta of x, just to make it simple. Okay? So an estimator is essentially a function of the sample, which is supposed to allow me to estimate, or to guess, or to... בעברית אני תמיד אומר, בטכניון קוראים לזה משערכים, למי שקצת מדבר עברית, ובחלקות הסטטיסטיקה בירושלים אנחנו קוראים לזה עומדים, או עמידה ושיערוך. מילים קצת מבלבלות, אבל אותו דבר. Okay, sorry. So we want this estimator to have some good properties. And of course, so this is the general setting, and of course there are many possible choices of an estimator. So in order to cast it into what we call Bayesian decision problem, we usually consider this, we map this into what we call the state of the world. So the state of the world is the parameter, possible parameters of my distribution. P, this is part of the statistical model of the Bayesian decision problem, with or without the prior. So if you are Bayesians, we actually assume a prior on the prior here, on the space of parameters. So we actually have a model of the joint distribution of the observations and the parameters. If we are non-Bayesian, we assume that somebody just picks theta somehow. And then in order to make it into a Bayesian problem, this is of course the observations as we have all the time. And this is our actions. Okay. So the actions, just like in the estimation of the state of the world in general, is an estimation of the state of the parameter from which the distribution was taken. Okay. And of course, in order to complete the picture, we need a cost function. So we also need a lambda, or small lambda, which is a function of our estimator, condition on the state. Okay, so this is, in estimation theory, we usually call it a loss function. But this is the same as the cost or risk or whatever that we talked in other way. Okay, so this is clear. So now we want to develop a theory, and of course I already showed you, I guess Noga even repeated it. So we usually are interested in two typical type of loss functions. Actually, in machine learning, we have expanded it for many, many others. But the classical loss function The first one is what we call the L2 or the least square, where the lambda theta condition, theta hat condition theta, is simply the norm, since this can be multidimensional, the L2 norm square, or the sum over the coordinates theta hat I minus theta I. Of course, this theta estimator is a function from the possible observations to the state of parameters. So the dimensionality is the dimensionality of the parameters. Okay? Should I say it explicitly? So theta hat is a function from the observations to the parameters, which is in this case the set of parameters theta. So this is simply the coordinate square, Euclidean distance, if you want, in the parameter space. Okay? And this is what we call the L2 or the square loss. Square loss. And in the square loss case, the base optimal can be explicitly calculated. And we did it. I'm not going to repeat the derivation. It's very simple. So the theta L2 or least square, or whatever, is of the sample is simply the what we call posterior expectation, or the condition expectation, which you write in this way usually, with respect to the posterior of theta. This is the Bayesian setting of theta. Or if you want, this is the integral of p theta, the condition, the posterior, which is what is the probability. If I'm a Bayesian, then I can in principle calculate the posterior distribution. I have everything I need. I can use Bayes' theorem. Posterior expectation of theta over all possible theta. It's very important. So here, the average of a theta. So this is an integral over the parameter space. And it's conditioned on the sample. But the sample is given. Though the sample was randomly chosen from the distribution, it's what we sometimes call in physics quench randomly, and we freeze it. We pick, if we take the axis to be fixed. So this is posterior expectation. At posterior, the average is done over the parameters. This is a headache in practice, because when you talk about a large number of parameters, and for example, again, neural networks. Now, it's actually very popular to talk about deep learning, things like this. So you have many parameters, thousands, hundreds of thousands, millions of parameters. Doing this expectation is a nightmare. It cannot be done. Not analytically and not numerically. And so usually what we do is all sorts of what we call Monte Carlo. I mean, we sample the space, but this is a nightmare for any practitioner. I mean, this is not something we like to do when we have a large number of parameters. Okay, so conditional expectation is a very nice thing in principle, and it's actually in some small problems it can be done. Gaussian mixture, quadratic regression, simple things. When you have a small number of parameters, small can be up to 10 parameters, then you are more or less okay. But we have what we call the curse of dimensionality, the number of points that, in order to sample this space of parameters, we essentially need, if we want to sample any square of size epsilon to the d, any cube in this space reliably, the number of such cubes grows exponentially with d. Okay? If I want to remain. So this is what we call the curse of dimensionality. This is bad. We need the exponential number of points in my Monte Carlo estimation or whatever, to actually estimate such expectation. This is not something we like, at least not in computer science. As I said, so we can estimate it, approximate it in various ways, and that's essentially what we're doing now. So the other one, so this was square loss. The other one, very important, is what we call the it looks formally as if we just punishing anything which is not exactly the parameter. So we're punishing, give uniform cost or uniform loss to the any miss. This is exactly the extension of minus delta chronicle that we said. It gave us probability of error. And as I said, I mean, when you see delta functions, you always need to think about it within an integral. And so essentially, I'm just plugging it in this integral, and the integral of the conditional risk. This is what I calculated here, essentially. So the conditional risk was an average over all possible thetas, parameters, states of the world, given the expectation, given the observation. This was conditional risk of the observation conditional risk. But when I plug this, it essentially selects out exactly the point which happens to this. So minimizing the loss, this gives us that minimizing the loss, the maximum, what we call the maximum posteriori estimator, is exactly the arg max, because of the minus there. I want to minimize loss, so it's the arg max of the posterior distribution. Okay, that's much simpler. Arg max of all possible thetas. So this is the best maximum a posteriori. Sometimes I actually want to do it, and there are people who made a career out of all sorts of efficient way of estimating maximum a posteriori. A lot of Amir Globusson work, for example, in the last years is around that. But in general, this is also not an easy problem. First of all, again, we're Bayesians here. We assume that we have a prior. So, but we know that this is actually equal. So here I'm going to assume IID. So IID sample. It's actually equal to the arg max of the theta of the log prior plus the log likelihood. Okay, is this clear? I simply use Bayes. And since the normalization is independent of theta, I don't care about it. Okay? And take log of course.
So the error of this estimator can only be 1 or 0?
The error is either 1 or 0. Actually, as I said, I mean, it's not the error is not 1 or 0. Of course not. I mean, but it's simply taking me. What do you mean the error? The distance between theta and theta hat. It's an expectation. The expected error is this. But you're right, I mean, it's kind of funny. And I took here the error to be 0 if I am at theta hat, and 1 or whatever I'm not at theta hat. If you really want to interpret this as some sort of a limit of this 1 minus delta ij that we had in the descriptives. But so essentially it's in some sense 0 if theta hat equals theta, and 1 is not really 1, but if theta hat is not theta. But this is the loss itself, but then I average it. So the conditional risk is averaging over distribution. This is not necessarily 1 or 0. You're right, it's a kind of funny creature. It's the probability. It's going to be the probability of theta. But the point is not what the value of the error is, but what is the estimate, what is the maximum. That's why I'm not looking at the maximum value of this. I'm looking at the arg max, which is the value of theta for which this is maximum. This is what I really care about. You are right. The conditional risk is simply the maximum theta. But that's a number that you usually don't really. I'm not really interested in. So this is already the thing that minimizes the conditional risk from maximizing that. Now, the point, the important point I made last time, is that as long as we are talking, so if I'm talking about IID, I didn't use it yet. So this is the arg max of the log prior plus the sum over my samples of the log txi given theta. So this is here I assume the independence. Okay, I turned the likelihood into a product and took the log of the product. This gives me a sum. Okay, this should be obvious to everyone here. So, but this, if I'm talking about independent numbers, this is going to grow linearly with them. Okay? It can actually, it's negative, but it's growing linearly. So, so asymptotically, as long as my prior is what we call proper, in the sense that it doesn't give 0 prior to any theta, and if it does, then exclude this theta from your space. I mean, if the prior doesn't allow it to be, then it's not what you want. Okay, so if this is proper, which means these are finite numbers and constants for any theta, then eventually the log likelihood is going to win. Okay? So asymptotically, theta, it's actually a bit tricky what I'm saying here. You have to be, you really want to do it carefully. So for large n, this is going to be very much like the argmax over theta of the log likelihood. So this is some sort of an approximation which depends on these two assumptions, that the prior is proper and that everything that I did so far is that taking the maximum of this will not affect the maximum. Actually, I have to assume more than properness. I have to assume that the derivative with respect to theta of the prior is okay. Because I'm going to use it, I'm finding the maximum by taking the derivative. So if the derivative is bounded, so it's a smooth and what we call proper, it's non-vanishing and smooth in some sense. So the derivative is not going to kill me. Okay, and this is what we call the theta ML, or maximum likelihood. Okay, so this is the maximum likelihood estimate. Now notice that I'm considering this function as a function of theta, not of x. I'm actually taking the derivative. So the likelihood function, strictly speaking, is a function of the parameter. I'm taking the derivative of the likelihood function with respect to the parameter. Actually, so in order to solve it, I mean, again, if the probability in the parametric family is well behaved, which is differentiable with respect to theta, so what I mean by that is that the function px given theta are differentiable function of theta. Actually, I usually assume twice differentiable, because we also want the Hessian, the second derivative. And so then essentially I know that an equation, what we call the likelihood equation sometimes, the likelihood equation, or the thing I actually solve in order to find the maximum likelihood estimate, is taking the derivative with respect to theta of this, or in general, the log likelihood, if I don't assume independence. This is true also if it's not independent. So the solution of this equation, the derivative, of course, there can be minima, and there can be subtle points, can be anything. But if I'm in a good family, of course, it's not usually not the case in any practical big problem. But if I'm a good family, this equation is actually an algebraic equation in theta that I can be able to actually solve numerically. And then actually we see, and of course in all the nice examples, all the what we call the exponential forms, you heard this already? Exponential families, I mean Gaussian, Poisson, Bernoulli, high square, all the nice things that you always see, always use. In all those cases, this likelihood function is well defined, and this is usually what I do. So this defines the solution of this is, for which this is true, it's a little abuse of notation, is this. This is the maximum likelihood solution. But you see that this is actually usually a condition for a local maxima in order to actually guarantee that it's a maxima, what should also be true. The second derivative is negative. Okay? So when we talk about actually condition for our estimated way maximum of the likelihood, we need to check the second derivative, or in the multidimensional case, we need to look at the Hessian matrix and to make sure that it's a negative definite matrix, which is usually we don't do it. It's a headache. Okay. Let's actually do it today. Okay, so this is the maximum likelihood estimate. In practice, this is the most useful or the mostly used estimator in statistics or everywhere. This is the first thing you want to try. Notice that this is not a Bayesian, not a strictly speaking Bayesian optimal estimator because I ignore the prior. So we want to try to define some good properties of this estimator. So at this point, I'm not talking about anything else. L2 and maximum procedure and then maximum level. The other things that we do in practice, and we'll talk about them in other places, like for example L1 minimization, not L2. L1 is actually turned out to be very important in practice because it's still solvable numerically with some efficient algorithms. So instead of taking the L2, I'm taking the absolute value here, L1. Turns out to have other nice properties like it gives us sparse solutions, and it's much more robust than the L2 estimate, and can be done. So this is something you're going to see in practice. There are many nice algorithms like lasso and things like this for estimating, for minimizing L1. Well, right, absolutely. Yeah. So I didn't say the word regularization yet, but this is exactly. So we cast we push the prior through the back door by calling it regularization. I usually try to be explicit about it. So if you have a square regularization, it's exactly like assuming Gaussian prior. We have a Laplacian regularization, or we have an L1 regularization. It's like assuming L1, but it's a different story. I mean, I'm talking about. Yeah, you're right. I mean, so you just open the door for something which we're going to discuss much later in the course. Okay. So, so at this point, what are the good properties of an estimator? So first of all, there are many examples that we need to see now, which I hope you're going to see through either reading it in the pages in the lecture notes or by doing the exercises. So I simply don't want to waste my time and start driving those simple things. But for example, one case which I do want you to all know. So for example, which is a canonical example. So if Px theta is essentially what we call normal with mu and sigma, one-dimensional normal, one-dimensional Gaussian distribution, you all know what it is. Which means that, let's write it once, 2 pi sigma e to the minus x minus mu square over 2 sigma square. Okay, this is the standard, not the standard, the Gaussian distribution in one dimension. Okay, so theta here is two-dimensional, is mu and sigma, or sigma square. So it's a two-dimensional set. It lives in the right half plane, and it's so mu can be anything. Sigma is usually positive. And if you actually calculate the maximum likelihood estimate for this, which you're supposed to do in your exercise, or at least saw it somewhere, then you see that mu hat, or this is my notation for the estimator of mu, is what? If I'm given a sample, so X is an IID sample. So this is the classical empirical mean. Okay, so this is very nice. It's natural, it's exactly what you expect. I mean, so if you're taking a sample, your best estimate of the mean of the distribution is the mean of the sample. Best in the sense of maximum likelihood. Actually, if there is, if you're looking at the maximum posterior, actually in this case you can calculate everything. All of them in one dimension, Gaussian. If you know how to do Gaussian integrals, then everything is relatively straightforward. I'm not going to do it here. But of course, if you remember the maximum likelihood estimate of sigma is going to be something like well, I'm careful because it depends if you're something else, n minus 1 over n, the empirical varies. It's a bit tricky, sigma square estimate. it's a bit tricky. So there's something here which I'm going to leave open. I wanted to see it also. But it depends if you're actually using the estimate of the mean from the sample, if you don't know the mu, or if you know mu. If you know mu and you don't know sigma, then you are in better shape than if you don't know also mu. And the estimator is slightly, so the factor of n minus 1 over n there, which corrects for that. So this I keep for the exercise, but this is simple. You can derive it essentially as I speak.
When would the mean never not be the optimal mean never not be the empirical mean? So isn't that like the definition when we take an empirical mean, the idea is that we're finding the mean of the true distribution?
The empirical mean is the empirical mean, which means I have samples. You can think about it as if you have an empirical distribution. And you expect you average the empirical distribution, not the true distribution.
Right, but as n goes to infinity, assuming that.
Okay. So you are running ahead of me. So of course, in order for this to have any value, so what do you know about such things? I mean, sums of random variables. So you know that this is going to have a distribution. So first of all, theta hat is a random variable. Okay? Why is it a random variable? I just want to make sure that you're all with me. Which means it has spread in general. Yeah, because I'm taking a sample. The sample is a random sample. Today you have one sample, tomorrow you have another sample from same distribution, same different numbers. And you're going to have a different value of theta hat. So even for non-Bayesians, there is always a probability distribution of theta hat given theta. This is a distribution. Of course, what it means here is that I implicitly average over the samples in some sense. But this is a distribution for a given sample. So actually, for a given sample, this is, so I actually do this chain. I mean, I sampled for the same parameter, different samples, and get then the different estimates. So I conditioned on theta, but not on the sample. And so this is distribution. And I know that in this case, let's say the probability distribution of mu hat is going to be the probability of a sum of average of an IID Gaussian numbers. So from elementary statistics, you know that this is going to have a mean, which is just a true mean, and a variance, which is what? What's going to be the variance of the estimate? The variance of a sum of an average of n IID Gaussian numbers. What is it? It's sigma squared is the original variance divided by n. The variance. The variance is sigma squared divided by n. The standard deviation is sigma divided by square root of n. This is something you have to remember in the middle of the night. Out of any, this is something you all have to remember. Okay, when I add some IID numbers, I get a normal distribution in the assumptions of the central limit theorem, which are very general for us. And this is going to have a variance which goes like 1 over n, and standard deviation goes like 1 over square root. Okay, so I know that in this particular case, mu hat is distributed with the same mean and variance that goes like sigma square over n. So this is a very nice. So I know two things. First of all, the mean of the estimator is the true mean. And of course, it's also going to be asymptotically correct. Asymptotically, the distribution of the estimator is going to shrink, like 1 over square root of n, and eventually it's going to be centered around the true parameter. So these are properties I really like. Okay, so I know that the mean is okay of the estimators, and that asymptotically I'm going to be with very high probability at the right value of theta. Okay. So these are the three properties we want to define. So one of them is what we call consistency. Which is an asymptotic property. It says that in improbability, the estimators for IID samples is going to be theta. Or if you want, theta hat of xn is approaching in probability with large n, and is approaching the true parameter. No, this is true. This is a property of an estimator for anyone. No, I'm just saying that the estimator is consistent. I mean, statisticians say that if the estimator is consistent, consistency means that asymptotically in n, I'm going to approach the right parameter. It's a very natural and actually a very weak assumption. So I want consistency. Now, the question is, what of those estimators that I mentioned here, which one of them are consistent? All of them maybe. But if you're getting an estimator, consistency, of course, this makes sense only in identifiable families, of course. Because if there's no one parameter, then it may converge to another parameter, which is exactly the same in terms of distribution, and there's no way I can tell the difference. Okay? So consistency is essentially what I really want is to show that the DKL of my okay, I'll show it explicitly in a second, and I prove it. So I want the DKL of P. I want Px given theta hat to approach in some sense Px theta. That's what I want. So if I say that, I don't really care which theta you pick. I want the distribution to be the same. And the way to say that is usually through the DKL between them, as we'll see in a second. Okay, so this is consistency. And then there are two other properties that I'm going to discuss after the break. One is called bias. So I said that my estimator is biased, or if you want, unbiased, if the expectation of the estimator, which is what I saw with the mu in the Gaussian case, is true always. It's true for my estimator. The expectation over the samples of my estimator is the true value of the parameters for any number of points in my sample. So this, then I call it an unbiased estimator, and I'll say it more carefully after the break. But then I also care about something called the variance of the estimator. So this distribution usually have an expectation and the variance. Okay, I said it in some cases actually all of it has if it's Gaussian. This is the only thing I really care about. It's going to approach, so it's completely characterized by the mean and the variance. But this is only in the limit, in the central limit theorem. In general, I care very much about these two moments: the variance and the bias of the estimation. So what I'm going to say again after the break is what are the general connections between these two things. And we talk about generally about what we call unbiased estimators, which seems like a very natural and very good thing, to have estimators for which the expectation is the same as the true parameter. And then we also like to reduce the variance as much as we can, because large variance means that for different samples I get different values of the estimator and going to scatter around. So if I want to reduce the variance, I need to average. That's usually what we do in any experimental setting. I mean, we average over many experiments. You want to reduce the variance, not to have any curve that makes sense. So all the experimentalists here should know that. But that's why we repeat experiments many, many times, assuming independently, and we average the result. And but what you're going to see is that there is a nice trade-off between these two things. So sometimes I can reducing the variance is actually more important in many cases. Actually, not reducing the variance, reducing the mean square error, which is again the thing that I really want to know. It's not the L2, but the mean square error, the MSE. And this is simply going to be the variance plus the bias square. And so there's a nice trade-off between the two. And this trade-off is actually deep in the sense that it really opens the door for all this notion of generalization. How do I do outside of my sample? And so we're going to talk about this, and then I'm going to talk about what is the minimum variance, achievable variance for any start with unbiased estimator. This is going to this has a very nice answer which is known as the Kramer-Rao bound. And it introduces another interesting concept, which is called the Fisher information. And so these are all things which are described in this in the lecture notes, but I'm going to do in the next hour. Okay. Questions? Everything is clear, or everything is completely unclear? I don't know. No questions. It's bad sign.
ליאור. אז בעצם אנחנו מגדירים את סעיפי החלטה, פונקציית החלטה שמתי אנחנו אני הקשבתי, זאת אומרת, אם משהו שהוא לא היה סתם זמן יעיל, אבל הוא לא יסבר לי, וזה גרם לי לחשוב שאני הבנתי משהו לא נכון. שבעצם אנחנו אומרים שיש איזשהו, יש אלפא ויש בטא, נכון? עכשיו, מה שאני
אלפא ובטא זה לא דברים שאנחנו עושים.
כן.
בראש אני אומר, אני רוצה לעשות מבחן, שאלפא ובטא
יהיו קטנים מי.
יהיו קטנים ממשהו.
כן.
אבל אני כן, זה מה שקרה דיזיין ריכוז. אני רוצה, זה שתוגנט מערכת, זה מה שאני אומר. תגנט מערכת לאלפא ובטא.
זה נכון.
אולי אני יכול. אני שואל אותך, אוקיי, כמה דוגמאות צריך בשביל להשיג את האלפא? זאת בעצם על שאלה אחת. בהנחה שיש לך מודל העולם, נניח בשתי השפות שניתן לחיים. אז אני שואל, אם אני רוצה אלפא ובטא של אחוז, נגיד, היא כולל הורית זה לא חייב להיות יותר שווה, אז אני שואל אותך מה הגודל המדגם המינימלי שפי. זאת בדרך כלל שאלה אחת.
לא מידה זה במסגרת התרגיל.
כן, בעקיפין כן. מה שבעצם אני אומר, בהפרעה סדרתית, הקצת תקבע בסופו של דבר, יש שני סופים, A ו-B. אני לא יודע, אני אומר, אלפא ובטא יש A של אלפא ו-B של חושב אותם במדע קשה.
כן.
אבל נתן לנו דבר שאלפא, A קטן מאלפא וקטן בעצם מאלפא כאחד מהבטא. יותר קרוב לאלפא גם זה נכנס אותו. ו-B גדול מאחד לשם כזה. זה מה שזה. זה אומר שאם אני עכשיו אחליט, אם אני אם אני אעבור את המבחן עם החצופים החדשים, אני מובטח לי שעברתי את אחד החצופים החדשים. התחלתי את החצופים החדשים, אז ודאי חצופים
זאת אומרת, לקחת חצופים שהם אבל זה שאני בוחרת אחד מינוס בטא, לא שזה...
אנחנו נתחיל לחצירות. אנחנו מסתכלים על הלוג לייקוד. לייקוד ריישו. אנחנו רואים שזה מתנהג כמו רנדום, ויש איזשהו סף A שתלוי באלפא ובטא. יש לנו סף B, אני מקבל את הספים האלה, יש קצת גלגול ברשימות, מה בדיוק B, מה בדיוק A, ולא חושב. אז אני יודע שהסף שמעל הקווים האלה נמצאים דברים שאמרתי. אחד מינוס אלפא ובטא. וכאן נמצא... כן, אני לוקח את הלוג של זה, הלוג של זה, הלוג של זה. באמת יש לי גם כאן שאתה גבול, ואי הלוג של זה. מסתכלים מסתכלים על הלייקד ריישו. לא על הלוג ריישו. שמעתי בזה שאי נוסף על הלייקד. עכשיו, אנחנו טוענים, עכשיו, מה שקורה גודל המדגם, זה גודל המדגם. גודל המדגם זה השיפוע של הקו הזה. אני יודע שאם כל פעם יש שני הספים האלה הם יותר גדולים מ-A ו-B ספורפי, אז אם אני אקח את אלה שדורים כזה, אני בוודאי ספציפי את A ו-B לזה. ובראש בנתי גם תולדות. צריך להמשיך. אבל מה שאני יודע שלסף היחס ספורטיבי הזה, השגיאה שלו, שאנחנו קוראים להם אלפא פרט ובטא, היא קטנה מהזמן. אז אני יודע שאני בסדר לגבי המשתתים האלה. את המשתתים האלה שאני אז עכשיו, מה קורה גודל מדגם? באמת גודל המדגם הממוצע זה נקבע על ידי היחס של DKL זה כזה. אז הוצאה, כן, לוג DKL זה גודל המדגם. עכשיו, בעל המהנדס אומר לו, אני רוצה אלפא ובטא, אם אני רוצה לעשות מדגם של 100 אותיות. זה לא טוב. כי אני יודע את הקידוש הספרות, אני צריך לנסות את DKL.
זה בעצם.
נכון? אתה רוצה לדעת מכונה מסוים דומה. פעם מסוים דומה יכול בתוך. מעשית, בשביל להגיע באמת לעצמות, אתה יכול לצפות את המערכת הפחות ממה שתגע. אז המבחן הזה הוא קצת בזבזני. אבל המעשתים האלה קצת בזבזני. ואם הדימון היא מאוד יקרות, כל אחד זה מוצא חדש. אז אני רוצה לנסות רק יותר טוב. אבל אם הדימון זולות, לפחות כזה שם מישהו שבונה. ובמערכת הפרוטורית שלנו, שאלה מה האינטגרציה שלי. כמה זמן אני מסתכל על משהו ואומר אני צריך לדעת זאת אומרת שמעתי יותר עושה אינטגרציה משפטית ואיזושהי תנועה שהיא מדמה דברים בליבי הדבר הזה יש לו משמעות תנועתית מאוד ישירה ה-DPL זה אומר ה-DPL זה זמן ההחלטה קצב ההחלטה אני רוצה להחליט מהר או שאני צריך יותר סביב אז אני רוצה יותר סביב או לחליפים זה רק יותר מותר.
ואז אני משלמת זמן.
בדיוק, השאלה מה יותר יקר הזמן או memory of one. לשפר את העין. Actually, so this sustainability is actually never met in practice. In any real model, it's actually very well, the method is really want this, but if I want this, I don't care. One of those historical instances of experimental statistics which should actually take up. I mean, it's really that people talk about efficiency. I think this is the most important thing. In that sense, that actually converts to true values of the process. I really care about this. No problem later. That's not the problem. Sometimes I know. For small models where you actually monitor the reliable case, so where the value of the process is good. Let's say I have a Gaussian distribution of the weight of my population. Get the true average. And that you actually give me the average. I mean, you tell me that the weight is 80 kilograms. This is the number that people use. People talk about the average income, the average intelligence, the average weight. These are the parameters that are famous. If you tell them no, whenever you say about the average income, about the average income, it's a very good way of cheating. But you're right that in many of the interesting machine learning examples, neural networks, we really don't care about the but if you take two experiments, there are cases, all the statistics that people talk about in in popular media, when you talk about average income or average votes or how many voters you need to talk about means of distribution. And you really care about the means, not about distribution. Most people don't even know that there is a distribution. And they take the mean, this is the true number. That's a very misleading statement, but they actually talk about the actual value of process. But you're right, that in practice we care about distribution. And this is what this is not this. We don't really care if we have different parameters. It has a meaning in the sense that it's a sample of Okay, let's go on.
The motivation is to see whether the neurons can learn without something. Because most, right, most current theories that do that are not. Yeah. Most people from the neuron is not linear and don't do that.
All right. So they're asking all sorts of good questions during the break. Some of the questions are important enough to be raised public. First of all, I just want to clarify this notion of consistency. First of all, it's really an archaic notion which should go away from the text. Because this notion that I actually estimated true parameters is something which nobody really cares about today in large models. But still, in simple cases, this is what we essentially use statistics for. When I tell you what is the average weight of the population, I give you the weight, I don't give you the distribution. I tell you 50 kilograms, and sometimes it doesn't mean anything, because it can be either 100 or 25, and nothing, 50, or things like this. But the mean is what many people, mean income, mean whatever, is something people care very much about. But this is usually under some hidden assumption that you actually talk about normal distribution around the mean or something like this, and then it makes sense to talk about the mean. But when you talk about parameters of a very large model, usually doesn't make any sense because nobody really cares about parameters. What we do care is this, that the statistical model that we estimate from our estimators is close enough to statistical. Now this is, I don't know, this is not a stronger assumption in the sense that this does not imply this, but it's a much more practical thing. So this is what I really care. I want that my statistical law, with which I'm going to work eventually outside of my sample, will be close enough to the true law. And I really don't care about value farms. Value farms is an old thing that we should really, in some sense, rewrite all of the statistics. So we're still using language and terms which come from the earlier 20th century, which are meaningful only for small dimensional parametric families. Now, so there is a theorem which is actually an important theorem because it tells us something. That, yes. Michael, sorry. Tell me. By the way, I haven't seen any of the lectures uploaded to the web, but they promised me to do it at some point. I don't know why. I mean, I installed the camera here and forced everybody to use it, but it's not under my control at this point. So Neely promised me to. Maybe they can't read what I write on the board, or I don't know, but they should. So the theorem is that under assumption of identifiability, or identifiability in the limit, as we call it, the maximum likelihood estimate, or maximum likelihood estimator, theta hat from an IID sample. Whenever I say this, I usually, unless said otherwise, is consistent. In the limit, and when in probability. Now, what we're actually going to show is this, and then use identifiability, but I don't really need it as a right. So the proof is very simple. Actually, it's very explicit in Amir's note, but there's some typo there that I want to correct. But essentially, so theta ml is the argmax of the theta of the log likelihood. Okay, which is actually this is a trick I've already used before. So what I want, this is the argmax. So I want to talk about the limit in n. So we'll calculate the limit and go to infinity of the argmax of the log likelihood. And here I do the first thing that I have to be careful about, which is switch between the maximum and the limit. So those of you who are sufficiently sensitive to mathematical arguments, this has to be verified. Why and when you can do this. But I will do it as a physicist without thinking twice. Okay? I put a question mark here. Justified. And then I'll use the fact that this actually is a sum. Okay? So in the IID case, this is the argmax of a theta of the lim and goes to infinity of the sum. You know, without losing anything, I can take this to be this. Sorry, I need this 1 over n here. As long as n is finite, I can do this, okay? And then take the limit.
All you did was just move the limit over instead of the limit of argmax and argmatic limit. That's between the left and right hand side.
Sorry? I didn't get it.
Because the difference between the left and right hand side of that equation is just move the limit.
Yeah, I exchanged the order of maximizing and limiting. If you are okay with it, then you have a problem. I mean, you have to be careful with such exchanges. But I don't want to get into the mathematical argument here. So essentially, if my limit is within this compact set and not on the boundary and things like this of theta, then I'm okay. If the estimator is on the boundaries or something beyond if I don't have a compact set of theta, then things can get a bit. You have to be a little more careful. But I'm not going to get into it. This is a technical point that mathematicians like to make a fuss of, but you have to be careful about it. Okay, but if I can exchange maximum with limit, and it's really a property of where is this limit going to be in my class of theta. But under some regularity assumptions which are technical, and I don't want to, usually in this course I don't get into such arguments. Okay? Just realize that Amir is making it very carefully there. So in this limit, this is the limit of the sum of 1 over n, the sum over my sample of the log life here. Okay? So remember, I took out the differentiation with respect to theta, or the maximization with respect to theta, outside of everything. And I'm just looking at this. But now I'm using the fact that my xi's are actually sampled from the true theta. That's very important. I mean, xn is sampled from pxn at the right theta. Otherwise, I don't know what it means consistency. So the truth is coming from one of the parameters. Okay? This is one of the assumptions here. So what I know is something which I already used when we talk about sequential decisions, but I added it a little bit. This is heated a little bit, obviously. Yeah. But it's what we call ergodic properties. Essentially, this sum over the sample, since each sample is going to appear in the sum with exactly its probability times n, so the number of times a value of xi will appear in this sum is proportional to the sample size multiplied by the probability of this value. Okay? So this is actually a very important argument that we use all the time. So this is going to be asymptotically in the limit. It's going to average over the distribution. That's why I can do it only in the limit. So here I'm using something called ergodicity. If you don't know what it is, don't forget about it. But this is the technical term for what I'm doing now. So I'm assuming that my sample, very long sample, is going to sample the right values of x's in exactly the right probability that they were sampled from. Which means that this is going to be the argmax over theta of the expectation, or the sum over the x's, sum or interval actually, of px given theta log, sorry, I had to be a little more careful here. Let's call this theta prime here. Sorry, this is something so it doesn't matter, yeah. I just, since I'm going to use the true theta now, I have to be very careful with this dummy variable. So, okay, all I did is just, I'm maximizing over the thetas, but I denote this by theta prime. Okay? Nobody's confused with that? So here, but now here I have px over theta prime, condition of theta prime. So this is a very, this is a line that you really have to make sure that you understand. So I took the sample, it's a very long sample, and I asked myself, okay, let's say, think about it, I bin x's, and I asked what is the number of x's that fall into a certain bin. And if they are all sampled IID from this distribution, it's going to be the sample size times the probability of the bin. Okay? So 1 over n, the number of times they appear in this sum, is precisely this probability in the limit. Is this clear to everyone? This is really the critical point here. Okay, so, but this is what? Now I'm already back home. I'm out of board. Okay, so. So this is what? It's almost, it's what we call sometimes coarse entropy or minus coarse entropy. It's the average of the log probability with respect to that I'm trying to estimate, average with respect to the true distribution. So this is precisely something like this. It's the sum over x, again, it's the argmax over theta, theta prime, of this sum over x's given theta, log, now I can write it as minus so I already, so I added, okay, minus just because I took 1 over the p, okay? Now, here, of course, the reason I want to write it like this is why?
You should do that
Argmin. No, if it's the minus, it's okay. Still argmax. And here I have plus the sum over px theta log px theta. This is something we later on we're going to call this the entropy, but this one doesn't matter. So notice what I did here. I added I took minus log p and added it again here. So it's all right. Check the algebra, which is, as you said, this is argmin over theta. If I take the balance of this, of the DKL between px theta and px theta prime. Argmin over theta prime. Because this is independent of theta prime. So the minimum is not going to depend on this. Okay? This is independent of theta prime. Okay. So the minimum is just dependent on this. A constant doesn't change anything to the minimum. To the point of the minimum, not to the value of the minimum just, but the argument of the minimum doesn't change. But this is nice. Because now I know that the minimum, okay. So essentially the minimum of this is what? if my theta is in the set of my parameters, which means if my distribution was really one of the theta, that's what I assume now. We'll call this realizable cases in other cases. So this is where my rule, my sample actually came from this one of those distributions. Then the minimum, this is about, with respect to all the family, everything in the family, the true theta is there. Okay? So if the true theta is there, what is the minimum? 0. Okay? So if the true theta is there, this is going to be 0 in what we call realizable case. Realizable case, which is another word for saying that theta, the true theta is in the set. Okay? By the way, if it's not in the set, then I know that my maximum likelihood estimate will find asymptotically the closest in this sense of DKL to the set of my parameter distribution.
What do you mean in the set or not in the set?
The assumption that I made here, that this assumption, that my samples came from theta. I'm sorry. Here I didn't have to do. My assumption actually came. My samples actually came from one of the thetas in the class. So let's say you assume that the weight of probability of people is distributed normally. Of course, it's only an approximation because weight is always positive and so on. But let's say that it's close enough. I mean, 5-10 standard deviations away, I don't care. But as long as so this is an assumption. And now, if I estimate, I just take 100 people and take the mean of the weight, I'm going to have an in this case, unbiased and consistent estimator of my weight. And it's going to be consistent because asymptotically I'm going to converge to the true Gaussian distribution. But if I actually know that it's not a Gaussian distribution, then I do something else. So essentially I actually proved here. So okay, so in the case of realizable, and of course, notice that what we said is exactly what I wanted to say, that the distribution is going to go to this in the sense that the dp x theta hat and dp x true theta is 0. So that's nice. But if you actually want the true parameter, you have to assume this identifiability story. This happens only if they are the same parameter. So using if identifiable, this means that theta hat equals theta. Theta prime equals theta, or in the limit, or theta estimator. The estimator is the argmin of this. The maximum is theta. But this actually is something I don't really need. This is enough. Okay. So as I said, I mean, if you're not in a verifiable family, forget about it. Now, notice essentially what we proved is that the theta maximum likelihood xn is equal to the argmin over theta of the KL divergence between the empirical distribution and the class. Okay, this is also an important observation, which I'm going to use later on. So, and the empirical distribution, what I mean by the empirical distribution, here the empirical distribution was sampled from my true family, but that's not necessarily true. The empirical distribution is the distribution of my sample. How do you actually write it formally? Have you seen it somewhere? So the empirical distribution, PE or P empirical, of X is essentially 1 over n of sample size n. It's 1 over n, a set of delta functions. This is the empirical distribution. This is a very formal. Those of you who studied something like signal processing or statistics or anything, you may have seen it before. So essentially, this is point sampling my data, and now simply accumulate. This is what I call the empirical distribution. In reality, in practice, what you do if this is a continuous parameter system, what do you do in all your experiments? You bin which means that let's say if I have a Gaussian distribution, two samples will never fall in exactly the same place. It will happen, probability is 0. Okay. So usually what you do is you divide it into some intervals, and actually it's a very interesting question how to divide it correctly or effectively. And then you ask how this is going to be x1 and x2. You discretize the distribution. Discretizing the distribution means that you bin it into intervals. And then you actually treat this histogram as the empirical distribution. This is what you do in practice. So in all your experiments, whatever you do, you look at the distribution of weight, or the distribution of height, or the distribution of income, or whatever it is. The income are more or less discretized, but let's say you round it to some number and then you bin it. Okay, so and then of course you have a histogram, not a sum of delta functions. But that's some sort of regularization. Sometimes we call it Poisson windows or things like this. You actually instead of taking a delta function here, I'm actually taking a small Gaussian or a small rectangle or something like this and sum it. And then this is going to look very much like a crummy, noisy version of the true distribution. So I'm going to have something like this. Maybe. And essentially what I know that in the limit, my maximum likelihood estimator is minimizing the KL divergence between my empirical distribution and the parametric class. So that's nice. In some sense, you see another interesting meaning to the KL divergence. It's some sort of a measured distance between distributions, which in this estimation case is actually telling me I can think about it as a projection. And we actually use the name projection. It's a special projection, we call it the E projection. When the empirical distribution is on the left side of the KL divergence, and the parametric class is on the right side, which is in the denominator of the log, then I call it E projection, if it's the other way around. So the distance, it's not a distance because it's not symmetric, and you should think, it's not certainly not a metric, it's not a symmetric distance. But what maximum likelihood is trying to do is to find the closest point in the set of the parameter to the empirical distribution. So again, geometrically, I don't know how many of you like geometrical argument, but I like very much. So if you think about the set of distribution in some sort of a compact space, actually it's not. It's compact, but it's not always so nicely behaved, nicely smoothed. And so this is my parameters, which means every point here is a different distribution. Okay? So it's a kind of bundle of distributions associated to this. And my empirical distribution is, let's say, is here. It's not one of them. What maximum likelihood is doing is looking for the point in this space which is closest in the KL divergence sense. Over all possible distribution in this class, it finds the point closest to it. So this is why we usually call it a projection. So maybe some of you saw the name projection in other cases. A projection is the closest, a projection from this point to the plane of the floor is the closest point in the floor to this point, which is also the vertical point. This is not necessarily right, but actually the empirical distribution is almost always outside of your class. It's going to be noisy. In the limit, in the realizable case, when n goes to infinity, this empirical is going to approach the set, which means that the bins are going to be very narrow, and you're going to see a Gaussian distribution.
What are the dimensions of
that projection?
No, that space. What is each dimension?
So this is actually a manifold of parameters. Manifold seen as some sort of a subspace of Rn in this case. Let's say in the Gaussian case it's half of the plane, theta mu. In the Poisson case it's a real number, positive number. In the whatever, I mean it's some subspace, compact or not compact of Rn. Actually, I can almost always compactify it, but that's a different story. Not always. It's actually and the projection here is take the empirical distribution and look at the point closest to it in your subspace. And that's exactly the meaning of this minimizing the KL divergence. So not only did we prove the consistency of maximum likelihood, we also found actually a much nicer interpretation of maximum likelihood as a projection to the space. Okay, so now, in the little time that I have, I want to talk about other properties, the two other properties which are bias and variance. As always, I underestimate the time that it takes to talk about it. That's my chronicle problem. I didn't learn it until now. I probably will never learn it. I assume that it's the time it takes to explain it is only twice the time it takes to read it. Which is wrong. Especially when you read it very fast. Okay, now, so usually I read the class in less than an hour. So 2 hours should be enough, but it's never the case. So, I want to talk about something called bias. So consistency is an asymptotic property. It's in the limit of large sums. Many of the things that we talk about are asymptotic in that sense. That is an easy limit. A lot of things behave nicer in the limit. But in practice, as you know, we have finite samples. We have finite data, and we have to make decisions or to get estimators based on finite data. So the first thing we want to do, to assume, is that the expectation of my estimator over the samples, or if you want the conditional expectations over the sample, which is essentially, sometimes we simply write it as the conditional expectation of theta. Theta is given theta, average over the samples. Okay, so this is the mean at a finite number of samples. Okay, so I have a finite number of samples here. I fixed n, but I'm averaging over many samples of this size. This is a bit confusing, because actually in order to do this average, you need many, many samples. But I fix n, I estimate the parameter for a given n each time, and then I average over many, many samples. So essentially, it's the mean of this distribution that I wrote before, the conditional distribution of the estimator given the parameter. So if this is equal, if this equals to theta, then we say that theta hat is an unbiased estimate. Okay? If this, then theta hat is unbiased estimate. Or in other words, it's unbiased or לא מוטה בעברית, מאוד חשוב שתכירו את המילים האלה, לא מוטה. And actually we can define the bias of theta hat given theta to be exactly the difference. The expectation over the samples of theta hat given theta minus theta. This is the bias. So unbiasedness means zero bias. Okay? The bias can be either way positive or negative or whatever. I mean, it's a multidimensional thing in general. Okay? Okay, so this is the bias. Now, it's nothing more than the expectation of this distribution that I mentioned before, theta hat given x hat. It's the mean of this. I'm not writing every word on the board because this will take me forever. So, using the board as I need. Okay, so the other thing that I care about is the variance of the estimator. So the variance of the estimator is again very naturally is again I take the estimator at a given sample and then average and calculate the variance over all the samples of my estimate. So which is what? So how is the variance defined? It's the expectation over the samples. In this case again, the samples are taken from theta of what? Of the estimator for this theta minus the mean of the estimator square. Again, the mean is respect to the same thing. Conditional theta. So it's just like any variance. The average, the mean square error, mean square deviation from the mean. Okay. So you see that there is some biasness. Unbiasedness is a very nice property. So again, the early days of statistics in the 30s and 40s of the previous century, people thought, or maybe even until the 80s, people thought that unbiasedness is very important. Mean is not. Notice, by the way, that consistency also implies unbiasedness in the limit. But it's unbiased for every n is a much stronger property. So consistency we usually like, but unbiasedness. Okay. So essentially what we really care about is some sort of combination of the two. What we really care about is this, what we call the mean square error, or MSE, and this is something you're going to see in many, many places, MSE, the mean square error, which is, it's not exactly what I call the square loss, that's very closely related to it. The mean square error is essentially the expectation, again with respect to the samples, of theta hat, not with respect to the mean of theta hat, but with respect to the theta square. So again, I average over a sample that I've taken from the same theta. So there is a true theta. And I really want to know what is the spread around the true theta. The true theta, not the mean of the theta. Now, there is an obvious connection between all these things, the variance, the bias, and the square error. And you can easily convince yourself, since I'm running out of time again. It's written, you can verify it yourself. It's written in the notes, verify it. So, it's easy to show. Which means that you can do the algebra yourself. The mean square error of theta hat is x, and for any estimator, is what? So essentially, I just tell you, here's the proof. What's in order to connect it with this, what is missing? I need to add and subtract the mean. So this is equal to the expectation over the samples of theta hat minus the expectation of theta hat, condition on theta, plus the expectation of theta hat, condition on theta, minus theta, square. I didn't do anything. But now I can use these two terms as my A and B and use the well-known relation, which I hope all of you know. So you take this and you square it. So it's this square plus this square plus twice the cross term. Okay? Okay, but the cross term is the expectation of what? Of the cross term is simply the expectation of theta minus the expected of theta twice. But the expected of theta is the cross term is always 0. Convince yourself with that. So this essentially equals to the variance of theta hat given theta plus the bias square for any n. Well, this is n is always here. So this is going to give me the bias square. This is going to give me the variance, and the cross term vanish. Convince yourself with that. That's the only thing I want you to verify. Okay, so this term is 0. It's easy to see. So this is nice, because you see that something that we really care about is how spread is my estimator with respect to the true theta is made out of two terms. One of them is the variance, and the other one is the square of the bias. Those of you people have seen this, you encounter this identity in many, many different shapes and forms in your education. I'm sure you saw it in mechanics, for example. It's called Steiner lemma, Steiner theorem in the center of mass. The square distances of a point is the distance of the square of the center of mass plus the variance around the center of mass, so on. There are many, many cases there you see exactly the same thing. So it's just a simple observation that it comes in many places. Okay, but this is important. So now notice, this is what we really care about, in the sense that we want to know how far, what is the spread of our estimator around the true theta. And we see that this spread is made out of two terms. One of them is the spread around the mean of this theta, of this estimator, and the other one is the distance between the mean of this estimator and the true theta, square. Now, in principle, from this point on, statistics went under the assumption that the bias is 0. Now we know that there's actually a trade-off. If in order to get the bias to be 0, I increase the variance too much, then I'm probably not in very good shape. Because, okay, maybe I have a 0 variance, but I need a 0 bias, but I need there's a huge spread to my estimator, which means that in practice, when I use this estimator, I'm going to get results scattered all over the place. So maybe if I actually add a little bias, I can reduce the total mean square error, and certainly reduce the variance. And this is precisely what happens, by the way, in most of machine learning. I mean, so we have a trade-off, which we call the bias-variance trade-off, or the bias-variance dilemma. We're going to find papers with this title in many places. And sometimes we actually want a model which is a little bit more restrictive, but so it has a bias. So let's say, how can I verify? How can I guarantee no bias at all? And let's start with the other side. How can I guarantee no variance at all? So if I restrict the set of my thetas, let's say I have a very stupid estimator. Whatever you give me, I return the same theta. Okay, theta 0, whatever, 1 point. No variance. The same estimator, the same parameter. Obviously, the bias is going to be very large. On the other hand, if I take a very large set, I reduce the variance to 0, but I can have, the bias to 0, but I can have, and then I will have a huge variance. So you can see that there's something in the set of theta, I mean, what is the size of my parametric family is actually very interesting. I mean, if I have a too large parametric family, I reduce the bias, but may increase the variance. If I have a too small parametric family, it's the other way around. So there's an interesting question here, which we'll come back to. It's a very important question. What is the optimal trade-off? I mean, where do I want to stop? Which is exactly, essentially, how large the family is going to be. This is what we call the model of the estimation problem, or the complexity control, or whatever. There are many names for it. So the secret is, or the insight behind it, that there is what we call no free lunch. I mean, in some sense, you cannot have both small. You cannot have both small in some sense, if you really want something that covers everything well, then you are going to have a huge variance and trade ratio. If you're going to want to cover everything with no variance, then you obviously have the wrong model. So this is going to be an important question, and the no free lunch theorem tells you essentially this in some other words. I mean, you cannot get something for nothing. You need data, and you need to assume something about your model. With no assumption, you cannot model anything. Okay, we'll come back to this, and my time is really off. So what is the next step? So the next step is to assume unbiasedness. So if we assume that the bias is 0, which is unbiased estimator, then what is the minimum variance? The minimum variance of theta hat. So this is the question that was asked a long time ago, almost 100 years ago, in the 20s, when the parametric statistic was established by Fisher and many other statisticians. Your names you'll see, Neyman, Pearson, all of those people. So essentially, there's a very nice answer to this. So it turns out that you cannot really minimize if the bias is zero. You can't really minimize it completely. So there is a theorem which I'm going to prove, but unfortunately not today. Theorem which is called the Kramer-Rao bound. Double M? Excellent. No, it's one M. Kramer-Rao, which tells you that the variance of any estimator, any unbiased estimator, is greater than a number is lower bounded by something, by 1 over n, some number, which we call j of theta, and this j of theta is called the Fisher information, which is nothing more than the expectation of the logarithm of px theta divided by theta squared. Okay, and this is called the Fisher information. Okay, so it's a bit scattered around, but this is the next goal. So we want to lower bound the variance by some number which depends only on the parameter theta and the family, of course. We want to say this family is actually very interesting for this particular distribution. Oh, we are going to characterize a certain class of distributions which are going to be exactly the exponential forms, for which this lower bound can be achieved as equality. So in statistics, we now say two things. One of them is unbiasedness, which is no bias. The other thing is minimum variance, which you also call, in statistics, you call it efficiency. So we said that an estimator is unbiased if it has no bias, and it's efficient if it has minimum variance. So what I'm going to show you eventually is that the maximum likelihood estimator, surprisingly, under very general assumptions, as long as they're talking about regular, twicely differentiable parametric families, he is both asymptotically consistent, this we showed already, and it's also efficient. So asymptotically, consistency actually implies unbiasedness in the limit. Not for every n, but in the limit. It's also going to be efficient asymptotically, which means it's going to achieve the minimum variance. So these are the nice three things that every engineer or every statistician will tell you. This is what's so good about maximum likelihood. It is consistent, and it's efficient in the limit, which means it's going to achieve the lowest possible variance. This is true for any maximum likelihood estimate. Now, we'll be interested in the distribution for which this can be achieved for finite n. These are very interesting classes of distributions. As I said already several times, these are the exponential forms, which include all the nice distributions that we all know from the textbooks. So those have something very special. They can be efficiently estimated, which means there's minimal variance. Now, okay, I'm out of time, but the proof of this, I really want you to read it. It's in Amir's notes. It's very simple. It's nothing more than applying Cauchy-Schwarz inequality, which I'm sure some of you have seen already. But it has to be done carefully. So I need to think about the properties of this logarithmic derivative of. So the logarithmic derivative is some sort of sensitivity. It tells me how much the log likelihood change when I change the parameter. So the higher the sensitivity, the better the bound. And this is actually why we use Fisher information, or many people use Fisher information to estimate efficiency of sensory systems. Maybe you see it in Yoram's courses or in Chaim courses, I don't know. I think that in the Reshatot Bet, you actually see the Fisher information. I'm not sure you actually give all the background. So I'm going to show you why is this such an interesting quantity. I don't really like to call it Fisher. I don't like to call it information. I think it's the wrong name for this. It's really sensitivity to the parameters. And in particular, the covariance matrix of this thing, which is essentially what's written here, it's So it has a multidimensional extension, and the covariance matrix of this thing is something which is turned out to be very important. It actually defines the geometric properties of my space, of my parametric space. And again, those of you who would like to think about geometry, this space of theta is actually a curved space. I don't know how many of you know differential geometry well enough to appreciate what I say. It's actually a Riemannian manifold, and it has geodesics. I mean, it has shortest distances in places, which are defined by the KL divergences. It has projections, and the local metric is exactly the Fisher score, the Fisher information. So it has all the properties of differential geometry, and we can actually play a lot of interesting mathematics with it. I'm not going to do it in this course, but I really love it. It's because it takes you to wonderful places. You can write equations for the curvature as a function of your learning, and so. Well, touch it a little bit. You already saw that this geometric intuition to think about projections, and to think about curvatures, and to think about geodesics and things like this is actually useful. It gives us some very nice intuition about statistics. Okay. So those of you who like this thing, enjoy. I'm here again next Wednesday. Okay.
So the same problem is actually the mean of that Gaussian variance.
It's actually going to be the estimator of the variance. The second derivative is exactly the Hessian metric.